Good
So
morning, sir.
today's good morning. Uh, today's lecture 5, and we just have introduced in the previous lecture about introduction to algorithm analysis, and we shall start very formally and in depth towards understanding algorithm analysis. So I have shared my screen, so hope you can see my screen. So yesterday, I mean, in the previous class, we just have been introduced introduced with, I mean, the formal definition of, I mean, big O notation, and and we and what is the big O notation? Okay, O notation is a kind of a measurement of performance of a particular algorithm. So if we know that we have learned that if the computational time function is given by Tn or Fn, for example, Fn, like this one. Yeah. So if any time complexity function Fn, okay, follows an inequality, satisfying an inequality relation, which is Fn less than or equal to some constant C into Gn, where C is some positive constant and Gn is another function of n. If n is a function, Gn is also another function. Here n is the problem instance, or you can say simply the number of data in the data structure, number of the size of the data structure, number of elements present in the stored in the particular data structure. It will be array, unit list, graph, tree, etc. That is n, and we must have this condition to be satisfied that n greater than equal to some positive constant in G. Okay, so for an algorithm, if a time complexity function Fn is less than or equal to C into Gn for some positive constant C, and n greater than equal to 0 for some positive constant in Gn, then we can say that Fn is equal to big O notation of Gn. And we understood this theory, I mean this definition, with the help of two examples. Okay. Now let's little bit understand what is the meaning of what are the two uh, complexity types, complexities aspect we have to think of. So you are judging an algorithm. We are judging algorithm. The evaluators are judging algorithms. Okay. So already you understand that to solve a specific problem, we may uh, we will apply our own approach to solve a single problem, right? And as our approaches will be different, naturally, the algorithm development will be of different structure. Logical part will be varying from one person to another person. Now, to solve that specific problem, okay, there will be a competition among the algorithms. So, which one, which algorithm will be better compared to the others? How can we evaluate that thing? Okay, this algorithm is better than the others. How to do that evaluation process? So, for that evaluation purpose, we may we may use these two important performance criteria. One is the time complexity, another is the space complexity. Okay, so let's talk briefly about space complexity. To space complexity, okay. So whenever we are writing a program, you are using Dev C++, for example. So you are writing the program on the Dev C++ editor, and when you are trying to save that file, that program, it will be saved in a file of which extension is .c or .cpp, sorry, .c file or .cpp file. So that is a file. So that file requires an amount of memory storage. Right? For example, a typical memory storage I will show you. Um, okay, this is the Dev C++. You are opening a new file, source file, writing something, and then you are saving it. Whenever you are saving the file, it is asking you to save in directory to a directory. Let's say I'm typing one, and extensions are like .c, .cpp, etc. etc. So I'm saving it, okay, closing it. That file is saved in my hard disk memory. This is that file. If I go to see the properties, it is showing me that it is occupying a 4 KB of memory size. That means 4096 bytes of memory. It it, uh, it is occupying. Okay. So the program is requiring some memory storage. Also in the program, also in the program, what you are I mean, so next, you are running the program. Compiling the program means you are checking, compiler is checking whether there is any syntactical error or not, etc. And any other errors, okay, yeah, present in the program or not. Okay, so if the compilation is successful, then you are running the program. So that is called the runtime thing. The time while you are running the program is known as the runtime of the program. And in the runtime case, it is taking some time to run the program. Also, it utilizes some memory to run the program. For example, I want to write a program to perform addition. Remember the very first class of your C language in the previous semester. You were asked to write a C program to perform the basic arithmetic operations. Addition of two numbers, subtraction of two numbers, multiplication, division, modular division of two numbers. So focus on a single such arithmetic operation. Let's say addition. So whenever you are doing the addition of two numbers, those numbers are getting stored in some memory allocation, memory location, right? For example, you want to perform A plus B, and you want to store that result into another variable C. So you are writing the code that C equal to A plus B. So A, B requires some memory storage, 4 bytes of memory. If the size of int is equal to 4, you know that typical memory size required for storing a single integer value is 4 bytes. So A requires a 4 byte of memory, B requires a 4 bytes of memory. Okay, and after doing the calculation addition A plus B, that requires another memory. Even if you do not do C equal to A plus B, only you are writing A plus B. Still, what is happening? Okay, temporarily, the value of A is being stored in a memory, some volatile memory. The value of B is also getting stored in some another temporary memory. They are being added. The result of A plus B is produced, and that result is temporarily stored in another memory. Though you are not doing C equal to A plus B, but still it will be done in the runtime. Okay, so A plus B will require certain memory space. Okay, so we are concerned about, interested on those space, how much space is being required in the runtime of a particular algorithm. So in case of data structure, it matters a lot. For example, I'm doing a searching operation. You know what is a linear searching? It is basic searching. What is a searching mechanism? And suppose already there exists a array, an array of let's say 100 elements, and I'm taking a value from the user. that value is to be searched throughout the 1D array. So what we are doing normally, that is the user given value, let's say x, that x is being compared one by one element in the 1D array. Okay, so how many comparisons we have to perform? Let's say, so if the size of the array is 100, so 100 number of comparisons we have to perform. So what is the comparison statement? That is, if x is equivalent to the corresponding array element or not. So that requires and it will give us another, and the result will be, uh, and the result after evaluation of the conditional statement. Okay, I'm sorry, logical statement. The result also requires some storage. Okay, so either true or false. If it is a boolean result, the condition is true or false. Okay, so this is a space all about. Okay, while doing temporary calculations. Also, in the runtime, what happens? That whenever you are creating an instance of an array, you are allocating memory for an array. Okay, that is happened during the runtime execution. You are writing int arr in bracket 100. That means you are allocating memory for an array of size 100. So when that memory will be allocated, when that memory, physical memory will be occupied, that is during the runtime execution of the program, not in the compilation. So if that memory is a large memory, let's say for linear searching, the size of the array is 10,000. So then time required by the program to complete the process of linear searching will be more as compared to the linear searching applied on a 1D array of size 100. The time will not be same, it will be different. So this is a very natural thing. We can convince ourselves, yes, during the runtime of the algorithm or the program, there is some variable involved in the algorithm. Let's say typically the size of the data structure. So the runtime or the computational time and also the space is depending on the size of the data structure, which is we called as problem instance of the algorithm. Okay, so this is very natural thing that yes, space will be required. More space. We do not want to say, for example, in today's scenario, we are I mean we are thinking about deep learning algorithm. So deep learning, the deep learning architectures. Okay. For example, YOLO C version or version 4. Okay, then ResNet, ResCNN. So this kind of deep learning models are not suitable for CPU, central processing units of our computers. We are using computers, laptops or desktops, and they have CPU. And today's deep learning models, which are advanced deep learning models, generative adversarial network, reinforcement learning based deep learning model, those models are not appropriate for CPU. Because if you want to run deep learning algorithm into CPU, in CPUs, they will take a longer time. So they request at least a minimum 16 GB of RAM to perform good. And also, not only the CPU, they require actually the GPU, that is the graphics processing unit. And also, um, uh, now the tensor processing unit is also coming into the picture. People are using this thing. So this is the computational aspect. Because the space is why deep learning is not appropriate for suitable for CPU, because it requires a good RAM, 16 GB, 8 GB RAM minimum, and also space complexity is a matter of concern. Okay, so for running to run a deep learning algorithm, you may require a large number of data sets. Large number of data set means I mean 50,000 data, 80,000 data. For suppose you have 1 lakh number of data images, not 1D array. Those are 2D array or 3D array. Each of the data is a single 2D array or 3D array, and the arrays are of dimension, let's say 256 into 256. That means in each of the 2D array, there will be 65,536 elements in each of the one 2D array. And you may require 1 lakh number of such 2D arrays. In each array, there are 65,536 elements. So out of 1,80,000 data you may require to train the deep learning architecture. Okay. So it requires a tremendous amount of space along with a tremendous amount of time. So that's why it is not appropriate for CPU. So GPU is what I recommend. So yes, so these are the things which are matter of concern today. Now coming to space complexity, so it is the amount of memory an algorithm needs to run to completion. Okay, let's illustrate space complexity of two algorithms to perform the following tasks. So I am presenting you a very simple problem, that is we are trying to find the summation of AI. Okay, some values, some elements. Suppose 10 elements are there, and we want to find out the sum of 10 elements or sum of 100 elements, like that simply. So this is denoted by mathematically summation over I equal to 0 to n minus 1 here. Okay, so Sn equal to summation over I equal to 0 to n minus 1 here, where I is equal to 0 to n minus 1. So this is the very simple problem. We want to sum up some elements. So addressing this problem, let's we can design an algorithm like this. So read n s equal to 0 for I equal to 0 to n minus 1, s equal to s plus ai, end for. Very simple algorithm. All of we can design this thing. Very easy. Now let's try to think about what is the space complexity of this algorithm. The space complexity consists of two things, two parts. One is a fixed part and there is a variable part. What is the fixed part? Typically includes instruction space, that is space for the code. Okay, space for fixed size component variables, constants, etc. Okay, for example here I equal to 0. 0 is a constant, 1 is a constant. Everything should be stored anywhere in a temporal memory. Okay, so those are fixed instances. For example here I, the variable I, that is a fixed instance. Okay, so it requires whatever the value of I, but the memory size of that variable I is fixed throughout the process. Okay, then a variable part includes variables depending on problem instances, recursion, and stack. So here the variable is n. N is given by n is the number of elements to be given by the user. That is the variable. So on the variable n, the algorithm performance, the space, total space required will be varied. Okay, depending. So now for algorithm 1, space for n, s, and I are fixed. Uh, okay. So here, okay. So let's okay, for this single algorithm, let's also consider n to be fixed. So n, s, I are fixed. Let's assume space or memory allocation for each of n, s, and I is 1 word or 1 unit. Okay. So how many variables are there? S, n, and I. Right. So s is a single variable of which value is getting changed, but the ultimate memory required for that s will be different. They will be same. Let me. So n is of integer type. So let's say it is taking 4 bytes of memory. and s is of another integer type, because we are if the elements ai if the elements I are integer, then summation of this ai will be of integer type. So let's say this is of 4 bytes of memory, and I is an integer, so it requires a 4 bytes. So total 4 into 2, that is 12 bytes. 12 bytes of memory is total required, okay, for the entire operation of the algorithm. Okay, so now where is the variable thing? So let's come to the point. Memory allocation of array with n elements is the variable. Okay, that is the thing. So let's say n equal to 10. So then you are creating an array. Then you are creating an array like this. So the array size will be 10 into 40. That is 40. 10 into 4, that is 40. So if this is changed, this total array size will memory size of this entire array will be changed. So in that regard, if you change n, then the space required by the algorithm will be different. Okay. Okay. So now, assuming memory allocation of each array element is 1 word, space required for the array will be n. Okay. So space complexity of algorithm 1 will be the value of n, memory for n value, memory for s value, memory for I value, and memory for the entire 1D array. Okay, that is n. So already there is n number of elements stored in one single array, that is your n. Assuming that 4 bytes of memory, 4 bytes of memory, whatever it's required, we are assuming that for simplicity purpose it is equivalent to 1 unit. 1 unit. So here 3 units and here n number of units. So total amount of space is n plus 3. That is written over here. So this is the space complexity of, this is the total space required for algorithm. It may be more than n plus 3. You see why more than n plus 3? Because the value of n requires 4 bytes of memory, because it is of integer type. This is of integer type, so it will require 4 bytes of memory. Okay, s is, but the thing is, the array elements may not be of integer type always. They may be of float type. They may be of some double type. So in that case, each of the memory locations of the array will not be 4 types. It will be more than 4 bytes. Okay, so this is the minimum amount of space. We can say that if, the true space required by the algorithm 1 may be more than that. So it's better to write that. Let's say space complexity of algorithm 1 is denoted by capital S in suffix algo 1. So then S algo 1 is greater than or equal to n plus 3. Okay, and you can see that it's a linear function of n. Right. Next, we know that SN, now think in a different way. This is your algorithm 1. The same expression SN equal to summation over AI can also be thought of in some other way. Like, see, so after expansion, what is that? The summation over AI is A0 plus A1 plus A2 dot 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 AN minus 2 plus AN minus 1. And in the next line, what we can write, see, AN plus 1 we are writing here, and the remaining portion A0 to AN minus 1 we are writing in the reverse manner, AN minus 2 plus dot 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 A2 plus A1 plus A0. This whole part, which is given in the first bracket, we can say that it is Sn minus 1. Sn means the sum of n number of elements, of which index starts with 0 and with n minus 1. So so if we exclude that an minus 1 from the remaining, the whole Sn summation, then remaining part is also a summation expression, and this is the sum of elements of which index starts with 0 and with n minus 2. So how many elements? 0 to n minus 2? N minus 1. So this is the sum of n minus 1 number of elements. So we can express that whole summation expression by a notation Sn minus 1. So we can write that Sn equal to An plus Sn minus 1. And this is nothing but a recursive statement. So we can't compute Sn if we do not have the ready-made value of Sn minus 1. And this is the recursion. And if you want to compute Sn minus 1, see, Sn minus, this is 1. So if Sn minus 1 is equal to, similarly, An minus 1 plus Sn minus 2. and Sn minus 2 is equal to An minus 2 plus Sn minus 3, and so on, dot dot dot. And finally, the last recursive line will be S1 equal to A1 plus S0, where S0 is equal to A0. So the same expression, Sn equal to summation over Ai, can also be thought of as a recursive model. Though these two approaches will give us same value, so these two approaches require different space. Is that true? Let's see. So the sum one can be computed using recursion. So algorithm 2. Based on the recursive statement, we are developing the algorithm read n, and we are defining calling a function calsum, passing the arguments, the array, and n. N is the number of elements. So calsum definition: if n is less than equal to 0, if the number of elements is, or the index is less than equal to 0, return 0. Or else, I'm calling recursively a function that is return an plus calsum a comma n plus 1. So this is the recursive function definition. By this, the same computation can be done. Is equal to summation over n. And now let's consider the space complexity of this algorithm 2 based on recursion. Fixed instances are n. N is a single variable which will hold a single value. It may be changed, but the memory size of that variable n is fixed. And depth of the recursion. Depth of the recursion is n plus 1. Depth of the recursion means how many times the recursive function call is being executed or occurred. Okay, and that is n plus. That is called the depth of recursion, and that is always n plus 1. Okay, so for visualization purpose, now in case of recursion, the concept of stack is coming into the picture. And what is that? See, so for example, this for the first time when the function calsum was called, so somewhere this statement, function calling statement, is stored in some memory. This statement will be stored in some memory. Let's say that memory is address is 8000H, where the function calling statement calsum an is stored. Now whenever this function will be called, there is a pointer in the in our computer processor, which is known as program counter. We will shortly understand what is program counter while studying a subject like processor and controller. So that program counter holds this memory address of the function calling statement. Okay, then from this function calling statement, the program control jumps from this address of 8000H to another random memory address where this function definition is stored, calsum function definition stored. It is not necessary that this function definition will be stored immediately after this function calling statement. That is true. Okay, so the program control switches its position from 8000H to any other memory address, which may not be contiguous to 8000. Okay, and there it comes. Okay, so calsum a comma n, and from here calsum a comma n, further recursive function call was invoked. Okay, so that is an plus calsum an minus 1. So this is another variable an. It's a value. So it requires a point. It's a memory, some memory to be stored an temporarily. So value pointed by a pointer. So it requires a address, a memory address. Then calsum, another function call, and let's assume that address of this function call is 7000. And what happens? This 7000 will be stored in the stack. Previously, let's say address of this function call is stored in the stack 8000, and above it, next function calling statement address will be stored 7000. Okay, So from this function called calcium a comma n minus 1, another next function, recursive function call will be invoked. That is a n minus 1 plus calcium a comma n minus 2. So this requires another memory storage a n minus 1, which is different from a n. These two are different memory locations, a n minus 1. Whenever the program will face a value for computation purpose, all the values have to be temporarily stored in some temporary memories. So n will be stored in some memory, n minus 1 will be stored in some memory. So calsum, it's a function calling statement again. So again, a function call is invoked and its memory address will be again stored in the stack, just above 7000, and so on, so on. It is keep going. So this stack addresses are extra as compared to algorithm 1. We have not seen anything like this in algorithm. So each of these function call requires storage of a pointer, that is to store an minus 1, n minus 2, and so on, referencing an array element ai. Okay, that is one thing. And the second thing is the value n or n minus 1 or n minus 2. This value, this this value n, this value n minus 1, this value n minus 2. All of those values are also requiring memory spaces to be stored. And third is the address of location from where the function calling is done. This is one function call, the first function call, second function call, third function call, and so on. This is fourth function call, and so on. N plus 1th function call. Okay, this is n minus 0, n minus 1, n minus 2, dot dot dot, up to it will be calcium a comma 0. So total n minus 0 to n minus n, that is n plus 1 number of function calls. That's why depth of the recursion is n plus 1. So for all those n plus 1 number of functions calls, each of the function call will require a memory address. So n plus 1 number of memory addresses which are going to be stored in the stack. Assuming each of them requires one word of storage, one unit. This is one unit, this is one unit. How many units? N plus 1 number of units we require in the stack. Okay. So n plus 1 in each of the n plus 1 function call, in each of the function call, we require the memory storage for a, we require the memory storage for n minus 2, okay, and we require the memory storage for the address of the function call. So this thing is required for in each of the n plus 1 number of instances function calls. That's why 3 for each function call, and there are n plus 1 number of function calls. So 3 into n plus 1. So this is the space complexity, and yes, the true space complexity can be more than this. So S algo 2 is greater than equal to 3 into n plus 1. Again, this space complexity is a linear function of n. But what we mean by this, after analyzing these two approaches to solve a single problem, same problem, we come up to this graph that this is the plot S algo 1, blue color. This is the blue color line, straight line. Both are linear functions, so both will be straight line. So S algo 1 is equal to, assume ignoring the greater than sign, S algo 1 is n plus 3, and S algo 2 is 3 into n plus 1, that is 3n plus 3. Though they are straight lines, but their slopes are not same. Algo 1 is little bit flatter, and the algo 2 straight line is steeper.
Steeper.
So it is growing more faster as compared to is I mean not faster. I mean it is growing more steeper. I mean it is more. I mean more monotonically increasing in nature. Okay, with respect to the problem instance n, the variable instance n is the number of elements in the data structure. So these are not same. The approaches are not same. So if I ask you, just compute the summation of 10 elements, read a 1D and compute the sum. The problem is so easy. And you may have two approaches. One is recursive, another is uh, non-recursive. Right? But in this case, what we can understand In terms of space complexity, the non-recursive method is better as compared to the recursive method. Okay, so this is a very simple problem I have used for demonstration purpose to understand what is actually space complexity and how to compute a rough estimation of the space complexity of an algorithm. We are not at all interested on the exact uh, expression of space complexity or time complexity. At least we must have a rough estimation. We must be able to come up to this portion. We must be able to sketch the graph of the complexity functions, space complexity or time complexity, and see how it is growing, how much it is increasing or decreasing, whatever. Okay. So we can observe for n greater than 0, S algo 2 is greater than, means it is greater than S algo 1. Oh, sorry, space is more than space in algo 2 is more than space is algo 1. So algo 1 is better in terms of space complexity. Okay, it's 11:17. Uh, okay, so we can stop at 11:20.
Sir,
Yes.
sir, which should we give preference to time complexity or space complexity?
So see, that will be that we shall come very soon. That we want every algorithm to be better in terms of space complexity and in terms of time complexity. Both, though both are the parameters for evaluating an algorithm, its performance. If your time complexity is good, but space complexity is not good, it's very bad. I can't say your algorithm is good. So your algorithm have to be good uh, both in terms of space and time complexity.
Okay,
And we
sir.
will,
Sir,
yes,
sir, if we consider the first algorithm, the value of n is same for the whole for loop. So why can't we judging it as a variable?
no,
We should.
we are considering the space complexity, not okay. So now, whatever be the value of n, even if you change or not, do not change, doesn't matter. This is n. You are changing the content of this variable. It doesn't matter. But the memory size for n variable is fixed for bytes. Whatever be the value, 1000, 100, 5,
Yes.
10. But if the value is changed, the array size is changed. Here is the space, what is changing based on the value of n. You got it?
Yes, sir, that's why we're calling it a variable.
Ah, that's why it is calling variable for this purpose. The array size is getting changed.
Okay.
Any other question? I think I will start a fresh time complexity in the next class from 12:30 because time complexity will I have to convince you people, so it will take some time. Why time complexity is thought like this, and we will shortly see that in some algorithm are performing better in terms of space, but not performing in terms of time complexity. Whereas the other algorithm is performing better in terms of time, but not performing better good in terms of space. And both the algorithms are solving the same problem. So that means it is natural that space complexity and time complexity are in some cases opponent to each other. They are opposite the performances of algorithms. So we have to compromise a little bit in terms of space and time complexity. And thereby it comes that there is a engineering comes perspective comes into the picture. We are engineers. Why we are engineers? What is our role? Engineers' role is to make a compromise in the performance. For example, I am using a mobile device. Okay. So I expect this mobile device to be more general as possible, but it is not possible. There is some limitation. Front camera is not so good in my mobile. Sorry, back camera is not so good in my mobile, but front camera is very good. It is using a very good image processing algorithm. It is clearing my picture of my face, etc., etc. So it's good. Front camera is good, but I want my back camera to be very good. But if I want my back camera to be good, the price of this device will be naturally increased. No, I can't afford that much price. So let's compromise myself. So engineers are creating a lot of versions. Okay, why? Based on different sacrifices, compromisations. There is always a trade-off. This is called engineering. There is no absolute kind of thing. As per the user's requirement, as per the customer's satisfaction, we have to devise, we have to design a lot of versions. Okay, and all are done based on the trade-off, engineering trade-off between parameters. In case our parameters are space and time complexity parameters, so we have to make a trade-off. We have to there comes an optimization. So we have to produce a device which is good in terms of space, which is good in terms of time. Both way I'm satisfying the customer. But I'm not designing a product or something which is best in time but worst in space. That is not at all efficient. So always there is coming an engineering trade-off, an optimization between space and time complexity. Okay, and this is the true meaning of an engineering perspective. Engineering. Okay, so let's stop the lecture. And if you have any doubt, you can ask me now. Thank you for the lecture. Excellent.